Well, after decades of studying it, Freeth finally revealed what he really discovered inside, and it's not what anyone expected.
In a small stretch of sea between Crete and mainland Greece lies the tiny island of Antikythera. In the early 20th century, a group of Greek sponge divers exploring the waters near this island made a discovery that would change history forever. While searching for sponges, they stumbled upon the wreckage of an ancient ship buried deep beneath the waves. Alongside statues, pottery, and coins, the divers found corroded bronze fragments that appeared ordinary at first. No one at the time realized that these small pieces of metal would later reveal one of humanity's greatest technological mysteries. These fragments, heavily covered with rust and green patina from centuries underwater, contained tiny teeth of gears, inscriptions in ancient Greek, and thin bronze plates that seemed part of a much larger, highly complex structure. Experts examining the fragments were stunned. The precision, sophistication, and intricate craftsmanship of these pieces were far beyond what had been expected from the ancient world. Over the decades, scholars and scientists would struggle to understand their purpose, giving birth to a mystery that has captured imaginations for over a century. The fragments eventually came to be known as the Antikythera Mechanism. At first, experts speculated it might have been a navigational tool, a simple calendar, or even an astronomical calculator. Yet, the corroded state of the bronze and the faint inscriptions made analysis extremely difficult. Scholars could see gears, but how they worked together remained a puzzle. For decades, the mechanism sat in the National Archaeological Museum in Athens, quietly holding its secrets. Advances in technology, however, eventually made it possible to look inside without damaging it. Using advanced X-ray imaging and three-dimensional scanning, scientists could finally see the interior of the device in unprecedented detail. These scans revealed that the mechanism contained at least 30 interlocking gears, each cut with remarkable precision. The device could track the movements of the sun, moon, and possibly planets. It could even predict lunar and solar eclipses and display the timing of games similar to the Olympics. The realization that such a device existed more than 2,000 years ago completely transformed historians' understanding of Greek science and engineering. Professor Tony Freeth, a mathematician and researcher, played a crucial role in uncovering the secrets of this extraordinary device. Freeth's unique combination of analytical skills and creativity allowed him to see beyond the corroded fragments. Trained in mathematics, he specialized in set theory, which helped him identify complex patterns and relationships. His curiosity extended beyond pure mathematics to filmmaking and science communication, giving him the ability to explain complicated concepts visually. When Freeth encountered the Antikythera Mechanism, he recognized that it was not simply an ancient tool, but a sophisticated mechanical model capable of representing the motions of celestial bodies. Over years of study, he analyzed the gears, inscriptions, and structure to reconstruct the device's functions. His approach combined modern technology, mathematics, and historical research, allowing him to reveal the machine's true complexity. Through his work, the mechanism was no longer seen as a broken artifact, but as a fully functional representation of ancient Greek scientific mastery. One of Freeth's most remarkable discoveries was the mechanism's ability to model the moon's motion. Unlike simple rotations or calendars, the device accounted for the moon's irregular speed across the sky, a concept only formally understood in modern astronomy centuries later. By using a pin-and-slot gear system, the mechanism could mimic the elliptical orbit of the moon, moving faster when closer to Earth and slower when farther away. This feature, connected to a gear with 223 teeth, also allowed the mechanism to predict eclipses accurately, demonstrating an extraordinary level of mechanical integration. The design showed that the creators understood the complex relationships between celestial cycles and could translate them into precise, interlocking mechanical movements. Each gear, dial, and inscription served a purpose, creating a miniature simulation of the heavens. This discovery revealed that ancient Greek engineers possessed not only observational skill, but also a level of mechanical and mathematical knowledge that rivaled modern engineering. Further research revealed that the front panel of the Antikythera Mechanism contained a complete cosmic model. Using digital reconstruction and imaging, Freeth and his team discovered 9 interlocking rings representing the sun, moon, and known planets, arranged according to ancient Greek geocentric beliefs. These rings, connected through nested tubes, likely carried small spheres symbolizing celestial bodies. with some possibly made of semi-precious stones to represent color or brightness. Turning the main handle allowed all spheres to move in harmony, replicating the movements of the cosmos in miniature. This mechanical universe demonstrated a deep understanding of astronomy, mathematics, and engineering. It showed that ancient scientists were capable of creating models that could track the heavens, forecast celestial events, and preserve knowledge for generations. The Antikythera Mechanism, as reconstructed by Freeth, emerged as a device far ahead of its time, a true analog computer to the ancient world. The Antikythera Mechanism's discovery and analysis have challenged assumptions about the technological capabilities of ancient civilizations. For centuries, historians believed that sophisticated mechanical engineering was a relatively modern achievement. The mechanism proved otherwise. Its gears, inscription, and dials reflect a level of precision, planning, and scientific knowledge previously thought impossible in ancient Greece. Freeth's work demonstrated that these ancient engineers not only understood astronomy, but could also translate it into functional mechanical form. The Antikythera Mechanism stands as a testament to human ingenuity and the enduring pursuit of knowledge. It reminds us that even in an era without electricity, computers, or modern tools, people were capable of creating devices that could calculate, simulate, and predict with astonishing accuracy. Through the combined efforts of archaeology, mathematics, and modern technology, the Antikythera Mechanism has become more than a relic. It is a bridge between the ancient and modern worlds. The work of Professor Tony Freeth and his team has allowed humanity to witness the ingenuity of Greek engineers, who over 2,000 years ago were able to observe, understand, and model the universe. Their achievement shows that curiosity, imagination, and scientific reasoning are timeless qualities that continue to inspire. The Antikythera Mechanism is not just an ancient machine. It is a message from the past, a reminder of human potential, and a symbol of the enduring quest to understand the cosmos. The Antikythera Mechanism is not just remarkable for its complexity, but also for the mystery of its origins. Scholars have debated who created it, when and why. While some suggest it may have been built by Greek engineers in the 2nd century BCE, others argue it could be older. The sophistication of the gears, the precise inscriptions, and the understanding of celestial cycles suggest that its creator had knowledge comparable to modern clockmakers and astronomers. It was clearly not a one-time experiment or a simple educational tool. Instead, the mechanism was designed to be functional, reliable, and accurate over long periods. This implies the existence of a culture of mechanical engineering in ancient Greece that has left few surviving records. What makes the mechanism extraordinary is its ability to predict astronomical phenomena. For example, it could model the cycles of lunar and solar eclipses. These cycles, especially the Saros cycle of 223 lunar months, are complex and require advanced calculations. That the mechanism could perform these predictions mechanically is astounding. Moreover, it tracked the irregular orb of the moon, demonstrating knowledge of elliptical motion long before modern astronomy formalized the concept. Its planetary dials reflected the Greeks' geocentric understanding of the universe, where Earth was at the center and the sun, moon, and planets revolved around it. The mechanism functioned as a complete analog model of the cosmos, a combination of mathematics, astronomy, and mechanical ingenuity. Professor Tony Freeth's contributions to unlocking these mysteries cannot be overstated. His mathematical expertise allowed him to identify hidden patterns in the device, while his knowledge of engineering and mechanics helped reconstruct its functions. Freeth led a multidisciplinary team of archaeologists, physicists, and engineers to scan, model, and analyze the fragments. Advanced imaging techniques, including high-resolution X-rays and 3D computer modeling, revealed hidden inscriptions and internal gear structures that had previously gone unnoticed. These inscriptions contain crucial information about the mechanism's purpose, including tables for lunar and solar positions, eclipse predictions, and astronomical cycles. Freeth also discovered the so-called eclipse engine, a part of the mechanism designed to track eclipses with incredible accuracy. By combining multiple gear systems, the device could calculate the timing, type, and even the direction of upcoming eclipses. This level of precision was unimaginable for a civilization without digital computers, calculators, or modern engineering tools. The mechanism's ability to combine multiple astronomical functions in one compact, mechanical device makes it arguably the world's first computer. It was not a machine designed for casual use, but a sophisticated scientific instrument capable of representing the universe in miniature. One of the most groundbreaking aspects of the Antikythera mechanism, uncovered through Freeth's research, was its ability to predict eclipses. This component, later referred to as eclipse engine, represented a level of sophistication previously unseen in ancient technology. By using a system of interconnected gears, the mechanism could calculate not only the timing, but also the type of eclipse, whether solar or lunar, and even the direction of the shadow across Earth. The precision required to achieve this is extraordinary. Ancient astronomers knew that eclipses follow predictable cycles, such as the Saros cycle of 223 lunar months, but translating this knowledge into a mechanical device required exceptional ingenuity. Freeth's discovery demonstrated that the Greeks were capable of applying mathematical theory to practical engineering, combining astronomical knowledge or mechanical expertise to produce a working scientific instrument. The design of the eclipse engine revealed more than technical skill. It also reflected a deep understanding of the relationships between celestial bodies. The same gear responsible for eclipse predictions also contributed to the lunar motion display, showing that the mechanism's engineers had created a fully integrated system. Every movement within the mechanism served multiple purposes, linking different astronomical cycles into a cohesive whole. This level of integration is remarkable, even by modern standards, and highlights the Greeks' ability to think in systems rather than isolated functions. Freeth's work revealed that the mechanism was not simply a static calculator, but a dynamic simulator of the heavens, capable of reproducing celestial phenomena in miniature. The eclipse engine thus became one of the key features demonstrating the device's function as the world's first analog computer. Another area of Freeth's research focused on what is now known as the lunar anomaly. Unlike a simple clock that moves at a uniform rate, the moon does not travel around Earth in a perfectly circular orbit. Its speed varies depending on its position, moving faster when near perigee and slower near apogee. Freeth discovered that the Antikythera mechanism accounted for this variability through the pin-and-slot gear system. This innovative design allowed one gear to slide slightly while rotating another, producing a non-uniform motion that perfectly replicated the moon's real orbit. By observing the mechanism in action through digital reconstruction, Freeth confirmed that the ancient Greeks had developed a mechanical solution to a problem that modern astronomers would formalize centuries later. This insight not only demonstrated advanced technical skill, but also provided evidence that ancient science had reached a level of sophistication comparable to modern understanding. The implications of this discovery are profound. It shows that the mechanism was capable of reproducing complex celestial movements with astonishing precision. Ancient engineers were not merely recording observations. They were translating them into mechanical motion. The lunar anomaly system demonstrates a deep grasp of geometry, astronomy, and mechanical principles, revealing a level of intellectual achievement that had long been underestimated. Freeth's work highlighted that the Antikythera mechanism was more than a timekeeping device or simple calculator. It was a miniature model of the cosmos, allowing users to visualize celestial events in real time. Through his research, Freeth helped the world recognize that ancient Greek engineers had created a machine that could simulate the heavens, predict eclipses, and model the irregular movement of the moon, all with bronze gears and ingenious design. While much attention has been given to back dials and lunar systems, the front panel of the mechanism contained equally astonishing discoveries. Freeth and his team at University College London used high-resolution imaging and 3D reconstruction to reveal a miniature representation of the known cosmos. The panel featured 9 interlocking rings, each corresponding to a celestial body, including Mercury, Venus, Mars, Jupiter, Saturn, the Sun, and the Moon. The rings were linked through a system of nested tubes that may have held small spheres representing planets, possibly made from semi-precious stones to indicate color or brightness. This arrangement allowed the mechanism to visually display the movements of celestial bodies as they revolved around Earth, consistent with the ancient Greek geocentric worldview. The mechanical representation of the universe was not decorative. It was functional, demonstrating the positions and motions of planets and stars in real time. The front panel's design shows that the Greeks were capable of combining observation, mathematics, and engineering into a single device. It illustrates their ability to create models that could represent abstract concepts physically and interactively. Turning the handle caused all the planetary spheres to move in harmony, reflecting their known motions in the sky. This integration of multiple astronomical systems in one compact device demonstrates an extraordinary level of intellectual sophistication. The mechanism provided a tool not only for prediction but also for teaching and visualization, allowing its users to understand complex cosmic relationships. Freeth's reconstruction confirmed that the Antikythera mechanism was a complete scientific instrument, bridging observation, theory, and mechanical execution. The Antikythera mechanism's discovery has profound cultural and historical significance. For centuries, the ancient world was often viewed as technologically primitive compared to modern society. The mechanism challenges this assumption, demonstrating that the Greeks possessed advanced mechanical and scientific knowledge. It reveals a society capable of translating theoretical understanding into practical engineering. The device also highlights the interconnectedness of ancient civilizations, as knowledge of the Saros cycle and eclipse prediction likely traveled from Babylonian astronomers to Greek engineers, who then created a functional model of the cosmos. The mechanism thus represents both the ingenuity of its creators and the broader transmission of scientific knowledge across cultures. The Antikythera mechanism is one of the most extraordinary inventions of the ancient world, a device so advanced that it continues to baffle modern scientists and historians. Discovered over a century ago by Greek sponge divers near a small island called Antikythera, this ancient machine lay hidden under the sea for more than 2,000 years. At first glance, it seemed like nothing more than a collection of corroded bronze fragments, covered in rust and marine growth. However, these fragments would later reveal one of the greatest technological mysteries in history. Professor Tony Freeth, a mathematician and researcher, dedicated much of his career to uncovering its secrets. Before his death, he admitted that the mechanism was far more complex than anyone had imagined and held knowledge of the cosmos that was centuries ahead of its time. The initial discovery of the Antikythera mechanism in 1901 transformed our understanding of ancient science. Divers found the remains of a shipwreck near the Greek island, containing statues, pottery, coins, and a mysterious set of bronze fragments. These pieces seemed ordinary at first, but upon closer examination, experts noticed gears, inscriptions, and plates arranged in a highly sophisticated manner. Historians and engineers were shocked, as nothing similar had been seen from that era. The device was broken into dozens of fragments, but the largest piece revealed visible cogs and wheels. Early researchers guessed it could be an astrolabe, a navigational tool, or an astronomical calendar. However, centuries of corrosion made it almost impossible to understand its exact purpose. The inscriptions were faint, and the complex gear system was hidden under layers of decay. It was not until modern imaging technology became available that the true genius of the mechanism was revealed. With X-rays and three-dimensional scans, researchers discovered that the device contained at least 30 interlocking bronze gears. Each gear had precisely cut teeth arranged with extraordinary accuracy. This suggested that its creator was not merely a craftsman, but an engineer with advanced knowledge of mathematics, astronomy, and mechanics. Freeth realized that the mechanism could track the movements of the sun, moon, and possibly planets. It could predict lunar and solar eclipses, and even display the timing of ancient Greek athletic games, such as the Olympics. Such sophistication demonstrated that ancient Greeks had mastered scientific principles that modern historians had previously thought were impossible for their time. Freeth's unique expertise allowed him to unlock secrets hidden for centuries. Trained in mathematics, particularly set theory, he had the ability to recognize patterns and relationships in complex systems. This skill was crucial in deciphering the mechanism. Unlike others, Freeth approached the device not only as an archaeologist, but as someone capable of reconstructing the logic behind it. By combining digital modeling with historical and astronomical research, he was able to rebuild the motion of the gears and understand how the machine functioned. His studies confirmed that it was capable of simulating the motion of celestial bodies with remarkable precision, essentially making it the world's first known analog computer. One of Freeth's most important discoveries involved the mechanism's lunar system. The moon does not move uniformly around Earth. It speeds up and slows down depending on its position. The Antikythera mechanism accounted for this, using a pin-and-slot gear system, allowing the moon's motion to be represented mechanically with extraordinary accuracy. Another gear, connected to the system, also controlled eclipse predictions, demonstrating that the device's designers had created a fully integrated instrument. This system was not a simple clock or calendar. It was a miniature model of the cosmos. Freeth's work showed that ancient engineers had achieved a level of precision and complexity that rivaled modern technology in many ways. Beyond the back dials and lunar system, the front panel of the mechanism contained a miniature model of the universe. Freeth's team at University College London discovered 9 interlocking rings representing celestial bodies, including Mercury, Venus, Mars, Jupiter, Saturn, the Sun, and the Moon. Some rings likely held spheres to represent planets, possibly made from semi-precious stones.